2a. Well, okay. Well, let's say this is the focal distance of the of this ocula, the eyepiece. We call it eyepiece. They call it ocula. It's the eyepiece of your microscope. And if I bring the this real image of this object, A1, I bring it inside. See, it's getting larger. It's larger than it started. If I bring it inside the focal point, you see, I create this virtual image, and look how tall that one is. I get this big magnification by bringing it in. If I bring it in even more, see, I don't get as much, but if I bring it really close, that's the way of magnifying it. I get this real image, but I need my eye to do that because the light is diverging. This won't project on a screen, for example. To project on a screen, I have to put the object outside, and then I get a converging beam. Through this is converging. I can put a screen out here and see it because you see the light is converging, and it will make a dot on a screen. But if you just want to look with your eye, all you do is put the object just inside the focal point of the ocula, of the eyepiece, and then you get a maximally enlarged. But your eye will do the focusing. See, the light looks like it's coming from there. It's passed through this lens, but it looks like it's coming from there, and this is where you'll see it appearing, and your eye will do the focusing of that. So that's how your microscope works. Okay, so that's the microscope, and that's let's see, do the magnifying glass. Was that sufficiently good? Let's go back to this one. Yeah, I hope that's clear enough. I think this one I can actually move to, right? For example, here's my focal point, and if I move the object inside the focal point, you see the rays look like they're coming this way. Looks like they started way out here, but it takes my eye over here to converge them and make an image on my retina. And by the way, the accommodation of the eye can be shown by this too. In other words, what you're doing is, let's say your retina is here. If you have a unfortunately this keeps. Let's try to think of at this point in space. Don't look at the screen here so much. Oh, wait a second. Maybe I can even use the screen. There's another way of doing this. Here's the screen. This is nice. So I can move the screen. So let's say that let me put the screen over here. Yeah, this will be like the eye, where the eye has, let's say, a focal point here. I'll put the screen here, and an infinitely far away thing will hopefully. Well, it's not infinitely far. Okay, here's your retina. Now the point is that as I bring something in, the light is focusing further and further behind the screen. So my eye would not see something here unless it accommodated. So how do I accommodate? In the case of the eye, I change the shape of this lens, this variable lens. I change the curvature. I need more curvature. I need less curvature. I have to make the lens fatter. If I make the lens fatter, I can bring the light to focus on the retina. So that's what your eye is doing most miraculously. So and when the object runs away from you and you focus over here, the eye will flatten out and it'll become a bigger radius and it'll refocus over there. So that's how you are. So you can play with this. I think it's really fun and you learn a lot. Okay, so we have the definitions here of the far point, which is the furthest distance you can see, and the near point, which is the nearest distance you can see. And you can, using just that information, you can figure out what kind of lens should you put in order to get the image to be where you can see it. And that's all we're doing with lens corrections. I don't want to restart. I'll ignore it. Okay, so what else can we talk about? Okay, so that's the magnifying glass. And there are formulas derived in the book based on these ideas. Namely, if you have a magnifying glass and you want the lens to be really near the focal point, and you want that to give you an image at a large distance, what will the magnification do to that lens? Okay, what else? Anything else to tell you about? Okay, well, that's good. I think that's pretty much what we want to know for the class. You know, but I did want to go back, if I may skip back a little bit. I'm really not satisfied with what we did about relativity. I think I didn't cover things in great detail, and at least enough clarity. So let me get rid of this, if I may. What I wanted to tell you a little bit more about relativity was is sort of the way that they make measurements. See, the books are a little bit obscure about what you're doing with relativity. See, the issue is we're dealing, of course, with two things that are moving relative to each other. So you have one frame of reference and another one that is moving with respect to it. And the question is, for example, how do you measure the length of something that's moving with respect to you? Talk to some of the people in the class about this. But that's not a terribly easy problem. Because if I'm standing still and something is going by me, how do I actually measure? Let's take a very big object so that I can't even see the beginning and end of it. How do I measure it? And it's running past me. So Einstein's way of thinking about it, you try to break it down to practical, semi-practical way of doing things. What he said is, okay, I can't do it alone. What I'm going to do is I'm going to get collaborators. I'm going to measure certain lengths, like a meter. And I'm going to put collaborators everywhere, in space, a certain known distance apart. And I'm going to give each of them a clock. And we're going to synchronize our clocks. I'll explain how we do that later. And we're going to measure the length of the moving object in the following way. As the object's going along, we're going to agree that all of my collaborators and I will look at our clocks. And at a certain time, let's say noon, we're all going to look straight ahead. And somebody is going to say, I see the one end of the thing, and somebody else down there will say, I see the other end. And we're going to call that the length of the moving object. Right? I mean, it's running along, and we have all these people infinitely close, by imagination, and we have the front and the rear. And we all agree that at noon, we're going to look forward. And so there's no time delay because I'm right next to it. And I see one fellow says, let's say number 362 says they see something, and number 225 says, I see the rear. And we take the length, it's 362 minus 225, just made up those numbers, and we get 337 meters long. That's one way of measuring a moving object. I don't know how else, it's a pretty reasonable way of doing it. Now the trick is, how do you get the clock synchronized? That's when the trouble begins. And Einstein has a scheme for that too. He said, let's do something like this. How do we synchronize the clocks? And he says, okay, let me do this. Let me start with some master clock. And I'm going to, hello, I know you. How are you? He's a gentleman from my gym. Welcome. Anyhow, so we're going to do this. We take a certain distance, which I said, let's say 3 meters. And I'm going to put clocks at every 3 meters, just for example. Because the time that light takes to go 3 meters is 3 times 10 over 10 to the 8 meters per second. So that's why I chose 3, so I can cancel out. It's 10 to the minus 8 seconds to go one unit of distance, 3 meters. So what I do is I do this. I start this clock at 0. I set this clock for 10 to the minus 8 seconds. It's not started, though. And I set this clock, which is this number 1, this number 2, this number 3. I set this for 2, 10 to the minus 8 seconds. And I set this one, I just put the hands there, 3. Okay, it's cute, isn't it? And what I do is I send out a pulse of light from here. And this clock starts running. When I send out the pulse, this clock starts running. So when it reaches, get rid of this. After one traverse, this clock has advanced 1 unit, 10 minus 8 seconds. The light has now reached this clock, and it starts running. And it's already preset at 1 times 10 minus 8. So it's in sync with this one. Then the light reaches this clock after 2 units. In the meantime, these guys are both advanced 1 unit. So they're reading 2. This one's reading 2. It started later, but it was set to go fast. And then this one starts when it reaches, and it starts. Actually, this started at 2, so it's advanced to 3 by the time the light has reached number 3. So now that one is started. And the light going the other way is the same thing. I put a clock here, preset at 1. This is the clock that may say the unit -1, -2. And this clock is set for 2. So when the light reaches here, it starts running. And that way you end up with all the clocks, all the hands pointing in the same direction. Right? And all the clocks are synchronized. That sounds pretty smart, right? So I preset the clocks this way. I get all my observers here, and the bar goes by. The fellows all look, and the clocks are synchronized. They just look, and when it's noon, everybody looks. The ones who are in front and back say, I see it. You find out who they were, and you've got the length. So that's a pretty foolproof method of measuring the length of an object. My friend leave? He doesn't like relativity. Talk to him about that. So now the problem is, and the problem with many of the things we're dealing with, is that in the other frame of reference, we said the clocks are not synchronized. And that's when the trouble begins. The point is, suppose you are in the frame of reference of the bar. And you watch this goings on in the other frame of reference, namely Mr. 0 here, Mr. 1, Mr. 2, Mr. 3, so on, Mr. -1, -2, and this -3 over here. Now, this bar, I think I imagined it was going this way. So from this frame of reference's point of view, these guys are going this way, right? They're going this way. Now, I watch what they're doing. Mr. 0 sends out a pulse of light in both directions. And this clock, I see this clock is already preset at 1, and this clock was preset at 2, and this clock was preset at 3. The problem is that from this point of view, the light reaches this clock first. So when the clocks have moved to, say, this position here, Mr. 0, this clock has moved to, say, well, let me see, about to here, and the light has just traveled, the light has traveled from this point out to here, and it strikes Mr. 1 and way early, and this clock starts running. This clock has barely moved because you see the light has traveled, say, this far. This guy's going fast enough, he's going to run into the light, and this clock will start running early. So this clock, see, he's between 1 and 2. He's between 0 and 1. I'm sorry, he's between 0 and 1. This clock has already started to run at 1. So this clock is ahead of this. And the one, Mr. -1 here, he's running away from the light, so the light won't catch him until later, so he won't start running until these fellows are further along. So they'll be going here. This one started too soon. He'll be like this. This one is like this. So in the direction that you're going, the clocks are out of sync. This one being slow, ahead, and more ahead. Now, when they measure the length, these folks say, I'm going to measure the length when everybody's at noon, but they're all at noon at different times. And that's what screws up the length of the thing. If you think this through, you realize that it changes it makes the length shorter. Because these fellows are moving, and for example, when this fellow, in this frame of reference, when it's noon, it takes, this fellow here is going to catch up later, and it will change the apparent length. I did want to say just a couple of things more about Einstein in a general way. If I have about 1 minute. Relativity, time point. The one thing I did want to say was that Einstein has been said to be the father of the atom bomb or something like this, or had something to do with the atom bomb. You want to have there were a couple of misapprehensions about what went on with him. Namely, what happened as far as the atom bomb was concerned was that he had colleagues who were aware that fission had been discovered in Germany, explained by Lisa Meitner and written up. And these scientists, Szilard and Fermi, wanted to warn the United States about the possible use of this as a weapon. And they weren't famous enough to make any impression. So these people went to Einstein and wrote, in fact, they wrote the letter, and he just signed it. And this letter was given to some close associate of theirs who also was a friend of, could walk into Roosevelt's desk and put it on his table, more or less, and bring it to his attention. So all Einstein said was, recent work by Fermi and Szilard has communicated to me that it's possible to make a weapon that might be very large, but might not be able to be carried by an aircraft, but it might be big enough, small enough to be carried on a ship. They didn't know how big it could be, and it would be extremely destructive. So he brought this to the attention of Roosevelt, and Roosevelt formed a committee to look into this possibility. So that was Einstein's total contribution to making the atom bomb. He was not involved with the project. In fact, he was rather suspect by the FBI. They had a dossier on him because of his leftist interests, and I think he had a Russian girlfriend. That's another story. And in fact, she was spying on him. But he was not involved, it turns out. But anyhow, as I say, he's a household world. You can buy baby Einstein things for your kids. They'll play music for him. And a very interesting thing that at the turn of the century, Time magazine picked the man of the century. It was Einstein. So, and by the way, relativity is often very much abused. People tend to say, in fact, there were some religious people who said he's destroying morals because everything is relative, and there are no absolute standards, there are no morals. Friends, it has nothing to do. Einstein's talking about relative things moving with respect to each other. It has nothing to do. Everything is not relative. In fact, I don't have that here. I have a list of things that are relative. Yeah, some things are relative, like position, time intervals are relative, lengths, mass, energy, but some things are not. The laws of physics are not relative. They're absolute. Einstein was a very strict believer that there was causality and there was a big connection between cause and effect. And the speed of light is not relative. In fact, that's a surprising thing. It's absolutely the same in every frame of reference. So his ideas have been abused, and you'll hear all kinds of crazy things in public, but be careful. It just talks about relative motion of things. Okay? Thank you. All right, we'll let the physicists take over now.